Today, we will explore the relationship between architectural form, building orientation, and environmental logic within the framework of passive environmental design. This topic is fundamental to understanding how architecture can respond intelligently to climate. Rather than relying primarily on mechanical systems for heating, cooling, and lighting, passive environmental design positions the building itself as a regulatory system. In this approach, climate is not treated as a constraint, but as a generator of form. Building form is not neutral. The geometry, massing, and surface-to-volume ratio of a structure directly influence heat gain, heat loss, airflow, and daylight penetration. A compact form may reduce heat loss in cold climates, while a more articulated or porous form can enhance ventilation in warmer regions. In this sense, form becomes an environmental instrument. Next, we consider orientation. Orientation defines the building's relationship with the sun and prevailing winds. Solar geometry determines which facades receive radiation and at what intensity throughout the year. A well-oriented building can maximize winter solar gain while minimizing summer overheating. Similarly, aligning openings with prevailing winds enables natural ventilation. Orientation is therefore not merely a site decision, it is an energy strategy. Finally, we address environmental logic. Environmental logic refers to the coherent integration of climate data, form, materiality, and spatial organization. It requires that architectural decisions follow a rational relationship with environmental conditions. When form, orientation, and envelope design operate together, the building performs as an adaptive system rather than a static object. In this lecture, we will examine how these three components interact and how early-stage design decisions determine long-term environmental performance. Ultimately, we aim to understand architecture as a mediator between human comfort and ecological context. Before moving forward, let us briefly clarify the learning objectives of this session. First, we aim to define urban morphology and understand its significance in sustainable urban design. Urban morphology refers to the physical structure and spatial configuration of cities, street networks, block patterns, building forms, and open spaces. Understanding morphology allows us to evaluate how spatial organization influences environmental performance. Second, we will examine how form and orientation directly impact energy behavior. The geometry of buildings and their alignment with the sun and prevailing winds determine heat gain, ventilation potential, and daylight access. These decisions are not only formal choices, they are environmental strategies. Third, we will explore how environmental elements such as climate, terrain, and vegetation shape urban planning and morphology. Cities are not abstract compositions, they evolve in response to environmental forces. Topography, wind corridors, solar exposure, and green infrastructure all influence spatial structure. We will also investigate passive design strategies related to heat, wind, and light. These strategies demonstrate how architecture and urban form can regulate environmental conditions without excessive mechanical intervention. Finally, we aim to apply bioclimatic logic at both site and district scales. Sustainable design is not limited to individual buildings. It must operate at broader urban scales to create resilient and climate-responsive environments. By the end of this session, you should be able to interpret urban form through an environmental lens and integrate climate-based reasoning into your design thinking. Urban form refers to the physical structure and spatial organization of cities. It encompasses the arrangement of buildings, street networks, plots, open spaces, and infrastructure systems. In other words, it describes how the city is physically constructed and how its elements relate to one another. However, urban form is not only about physical configuration. It also reflects how the built environment is shaped, organized, and experienced across different spatial scales. At the building scale, it involves massing, height, and orientation. At the neighborhood scale, it includes block patterns, density, and public space distribution. At the urban or regional scale, it addresses connectivity, land use structure, and spatial hierarchy. Understanding urban form is essential because spatial configuration directly influences environmental performance, mobility patterns, social interaction, and energy consumption. The way streets are aligned affects wind movement. Block dimensions influence solar access. Density impacts resource efficiency. Therefore, urban form is both a physical and environmental framework. It provides the structural foundation upon which sustainable and climate-responsive design strategies can be developed. Let's start with the question, what is urban form? Simply put, urban form is the physical structure and organization of a city, the way its buildings, streets, open spaces, and patterns of activity come together to shape the urban environment. We can understand it through several essential dimensions. The first one is physical structure, which includes buildings, their form, height, and typology, along with the street and circulation networks, the arrangement of blocks and plots, and the open and public spaces that connect everything. Then we have spatial configuration, which describes how spaces relate to each other, how streets are laid out, how accessible and connected different areas are, and how local and global spatial structures link together. Another important aspect is density and intensity. This deals with how compact an area is, population and building density, and how these relate to services, infrastructure, and people's perception of space. Land use pattern defines how space is used, whether it's residential, commercial, industrial, or a mix of uses within one area. Next, building typology looks at the types of buildings that make up the city, from detached houses and terraced housing to high-rise apartments or mixed-use buildings. And finally, we have human-space relationships, which go beyond physical form. This layer focuses on how people use spaces for living, working, and moving, how they perceive space, and how ownership or control, public or private, shapes the way cities function socially. So overall, urban form is a complex interaction between the physical, spatial, and human dimensions of the city, and understanding these layers helps us design more functional, efficient, and livable urban environments. Now that we understand what urban form is, let's look at its different types, which illustrate how cities evolve according to density, function, and geography. The compact urban form is dense, mixed use, and highly walkable, often associated with sustainable cities where housing, work, and services are close together. In contrast, the dispersed or sprawl form represents low-density, car-dependent development, typically found in suburban areas where distances are longer, and accessibility depends on private transport. The polycentric urban form includes several centers rather than one, promoting regional balance and reducing congestion in a single core. Then we have the grid-based urban form, which follows a regular street network with high connectivity, a form that supports clear orientation and efficient movement. The organic or irregular form comes from historical growth, with curved, narrow streets that have developed over time, often seen in older European towns. Finally, the linear urban form occurs when development follows a main axis, such as a transportation corridor, river, or coastline. Each of these types represents a distinct urban logic, reflecting how cities respond to social demands, topography, and environmental conditions. Together, they help us analyze how urban form influences sustainability, mobility, and overall quality of urban life. When we talk about orientation in urban design, we are really talking about how buildings and streets interact with the sun, and how that interaction affects comfort and energy performance throughout the year. Orientation determines both the duration and intensity of solar exposure, as well as how shade is distributed on streets and facades. In other words, it defines when and how spaces receive sunlight or remain shaded, shaping not only visual comfort but also the thermal quality of the urban environment. In general, north-south oriented streets tend to offer more balanced and stable shading conditions throughout the year. They receive moderate sunlight, avoiding overheating in summer while still allowing winter sunlight to penetrate. Meanwhile, east-west orientations experience stronger seasonal contrasts. They tend to get too much sun in summer, which can cause overheating, while in winter, controlling solar gain becomes less effective. So, orientation is not just a spatial or aesthetic decision. It directly influences the energy efficiency, comfort, and environmental performance of urban spaces. By controlling how the sun reaches buildings, designers can reduce cooling demands, improve lighting, and create more livable environments. Now let's take a look at the role of orientation in urban design, and how it contributes to energy efficiency. Orientation essentially determines how buildings and streets interact with the sun. It affects both the duration and intensity of solar exposure, and also how shade is distributed across facades and public spaces. When streets and buildings are oriented in a north-south direction, they tend to experience more balanced and stable shading conditions throughout the year. This provides a more comfortable thermal environment, with steady sunlight that supports passive design strategies. In contrast, east-west oriented streets face stronger seasonal contrasts. They receive excessive sunlight during summer, leading to overheating, while in winter they are less effective in capturing solar energy for warmth. So, even though orientation may seem like a simple geometric decision, it actually plays a major role in achieving greater energy efficiency and outdoor comfort in urban environments. Environmental logic is about designing cities that work in harmony with natural systems rather than against them. It emphasizes a systematic, rational, and integrated approach to urban planning, one that respects environmental processes, ecological limits, and long-term sustainability goals. This means that from the very beginning of the planning process, environmental conditions are treated as guiding principles, not as constraints. Factors such as climate, topography, water, vegetation, and soil are considered early on, shaping how cities grow, how infrastructure is placed, and how spaces function. By integrating environmental logic into design decisions, we can create urban environments that are resilient, adaptive, and sustainable, capable of maintaining ecological balance while supporting human life. So in short, environmental logic transforms planning from a purely technical act into an ecological dialogue, where every design choice contributes to the long-term health and sustainability of both people and the planet. Environmental logic in urban planning emphasizes a way of designing and organizing cities that respects the limits and processes of the natural environment. It's not just about adding green elements later, it's about integrating the environment from the earliest stages of planning. The first principle is exactly that, the integration of environmental factors early in the design process. This ensures that land use, infrastructure, and open spaces evolve in harmony with natural systems. Second, environmental logic relies on systems thinking and interconnection, recognizing that the urban environment functions as a complex network where land, water, vegetation, energy, and human activity all depend on one another. It also highlights respect for ecological limits, meaning designers must plan within what ecosystems can sustain. This is supported by the integration of planning tools and governance mechanisms, encouraging coordinated efforts between institutions and disciplines. Environmental logic also brings in a spatial dimension, the idea that the physical form of cities should reflect environmental performance, responding to microclimate, solar access, and natural flows. Importantly, it adopts a long-term perspective, focusing on sustainability and resilience rather than short-term growth. And finally, it seeks balance between development needs like housing and infrastructure, and environmental protection and social equity. So it's about finding equilibrium between progress and preservation. These principles directly influence how we manage energy and water in cities. Environmentally logical planning aims to reduce overall energy consumption, minimize dependence on energy-intensive infrastructure, and avoid spatial forms that lock cities into high energy use. Here, energy efficiency is treated as a structural and long-term goal, not as an add-on, but as something embedded in the urban form and its systems. This means orienting buildings and designing compact, mixed-use areas that naturally reduce energy demand for transport, heating, and cooling. When it comes to water, the same logic applies. Efficient water use is promoted through careful planning decisions that avoid excessive consumption, protect water-related ecosystems, and integrate natural drainage and conservation into urban strategies. In essence, environmental logic encourages cities to behave more like living systems, adaptive, efficient, and sustainable. By aligning energy and water management with ecological processes, urban design becomes not only functional but also regenerative. Passive environmental design is about using the natural characteristics of a site, such as climate, sunlight, and wind, to achieve comfort and energy efficiency without relying on mechanical systems. It all begins with climate analysis, which forms the foundation of the design process. By understanding solar radiation and local climate conditions, designers can make informed decisions about orientation and facade design. The building form itself affects how much heat is gained or lost, while the surface-to-volume ratio determines how efficiently a building can regulate temperature. Proper orientation helps optimize seasonal solar performance, capturing sunlight in winter while minimizing heat gain in summer. Shading devices such as louvers or overhangs play a crucial role in controlling unwanted heat. Similarly, thermal mass helps to stabilize indoor temperatures by absorbing and releasing heat throughout the day. Natural ventilation provides passive cooling by taking advantage of prevailing winds, while daylighting strategies reduce the need for artificial lighting. The building envelope, including walls, roofs, and glazing, works as a regulator, managing heat transfer between the inside and outside environment. Site conditions and microclimate also shape how spaces are organized. That's why early design decisions are so important. Choices made at the beginning of a project determine its long-term energy performance. Ultimately, integrating these passive strategies supports both thermal comfort and sustainability, creating buildings that naturally respond to their environment, smart, efficient, and harmonious with the climate. To conclude this part, let's look at a powerful example that brings together form, orientation, and environmental logic: the Salk Institute by Louis Kahn in La Jolla, California. The building's form consists of two perfectly symmetrical concrete blocks that frame a central courtyard. The composition is compact and monumental, expressing both functionality and spiritual clarity. The open courtyard at the heart of the complex acts as a void between two solid masses, creating a strong sense of balance and unity. In terms of orientation, Kahn designed the courtyard to face directly toward the Pacific Ocean. This careful alignment frames breathtaking views but also serves a climatic purpose. It captures coastal breezes and directs natural ventilation through the site. The daylight penetration is precisely controlled, defining the spatial quality and mood within the laboratories and offices. When we examine its environmental logic, the design creates a microclimate within the courtyard. The exposed concrete structure not only gives the building its raw aesthetic but also acts as thermal mass, absorbing and releasing heat to stabilize interior temperatures. Most importantly, natural light becomes the primary spatial medium. It organizes movement, shapes experience, and connects the human scale to the natural environment surrounding the site. Through this project, Louis Kahn demonstrated how form, orientation, and environmental logic can coexist harmoniously, creating architecture that is both universal and deeply rooted in its place. Another remarkable example that illustrates the relationship between form, orientation, and environmental logic is the Institut du Monde Arabe in Paris, designed by Jean Nouvel. The form of the building is rectilinear and compact, emphasizing clarity and precision in its geometry. It stands as a powerful modern structure that still manages to embody cultural identity through its materials and facade design. In terms of orientation, the building's southern facade is the key element. It is highly exposed to solar radiation, a challenging condition that Jean Nouvel transformed into an opportunity for innovation. Instead of blocking sunlight with conventional shading systems, he designed a facade that dynamically responds to it. Here, environmental logic is expressed through advanced technology inspired by tradition. The facade integrates light-sensitive mechanical diaphragms that open and close in response to changing daylight levels. This system reinterprets the traditional mashrabiyah screens of Arabic architecture, merging cultural heritage with modern engineering. The result is a facade that acts as a living environmental filter, controlling light, heat, and views while maintaining an ever-changing visual experience. It's a perfect example of how architecture can balance technological innovation, cultural meaning, and environmental performance within a single design concept. Through this project, Jean Nouvel demonstrates that environmental responsiveness doesn't have to be hidden in technical systems. It can become the architectural expression itself. Our final case study is one of the most iconic examples of architecture seamlessly merging with its environment, Falling Water by Frank Lloyd Wright in Pennsylvania. The form of the house is defined by bold, horizontal cantilevered terraces that extend directly over a natural waterfall. Wright designed the structure to grow out of the surrounding rocks and forest, creating an organic composition that blurs the boundaries between architecture and nature. Every element feels anchored to the site, not placed on it. In terms of orientation, the building is carefully positioned according to both topography and solar exposure. Its layout follows the natural contours of the land, allowing the structure to engage directly with the landscape. The terraces capture sunlight and views from multiple directions, creating dynamic spatial experiences while maintaining shading and passive ventilation. The project's environmental logic is equally remarkable. Wright used operable openings throughout the house to enhance natural airflow, minimizing the need for mechanical ventilation. The stone masses of the structure act as thermal buffers, maintaining comfortable indoor temperatures by storing and releasing heat. And most importantly, the integration with the surrounding forest and water features makes the building a living example of harmony between human design and the natural ecosystem. Falling Water embodies the essence of sustainable design before sustainability was defined. It's not just a house in nature, it's a house of nature, shaped by environmental forces and perfectly balanced within them. Together, these three projects, the Salk Institute, the Institut du Monde Arabe, and Falling Water, illustrate different interpretations of the same principles: form shaped by orientation, and orientation guided by environmental logic. Each project transforms environmental awareness into spatial beauty, reminding us that sustainable urban and architectural design is not only about efficiency, it's about harmony, identity, and the enduring dialogue between people and place. To wrap up the presentation, here's a brief reflection on what we've covered. Urban form shows us how the physical and spatial layout defines urban life. Orientation logic reminds us that the sun and climate are silent partners in design. Environmental logic takes this further, linking ecological processes to planning decisions and long-term sustainability. With passive environmental design, we saw how simple natural principles can create comfortable and efficient spaces. Through our case studies, the Salk Institute, Institut du Monde Arabe, and Falling Water, we observed how great architecture unites form, environment, and purpose. In essence, sustainable design isn't just about technology or energy, it's about harmony between people, place, and nature. That's the fundamental lesson connecting all these ideas.